In line 1, fn main open curly brace, the fn keyword begins a function definition. The entry point to all Rust programs is main. It takes no arguments and returns no value. Code blocks, also known as lexical scopes, are defined with curly braces. Footnote 1. This isn't technically correct, but is accurate enough for now. If you're an experienced Rust programmer skimming through this chapter, you'll know that main returns unit by default and can also return a result. In line 2, let a equals 10, we use let to declare variable bindings. Variables are immutable by default, meaning that they are read-only rather than read-write. And finally, statements are delimited with semicolons. In line 3, let b colon I32 equals 20. You can designate a specific data type for the compiler. At times, this will be required, as the compiler will be unable to deduce a unique type on your behalf. In line 4, let c equals 30I32, you'll note that Rust numeric literals can include types annotations. This can be helpful when navigating complex numerical expressions. And in line 5, let c equal 30_I32, you'll see that Rust permits the use of underscores within numeric literals. These increase readability but are insignificant to the compiler. In line 6, this expression, it should be easy to see that calling functions looks like what you've experienced in most other programming languages. In line 8, in this expression, println exclamation point is a macro, which is function-like but returns code rather than values. When printing to the console, every input data type has its own way of being represented as a text string. Println exclamation point takes care of figuring out the exact methods to call on its arguments. Strings use double quotes rather than single quotes. Rust uses single quotes for single characters, which are a distinct type, char. And with Rust, string formatting uses curly braces as a placeholder rather than the C-like printf style of %s or other variants. Finally, in line 10, in this expression, you can see that Rust syntax for defining functions is similar to those programming languages that use explicit type declarations. Commas delimit parameters, and type declarations follow variable names. The dagger, or thin arrow syntax, indicates the return type. Section 2.3. Numbers. Computers have been associated with numbers for longer than you have been able to say formula translator. This section discusses how to create numeric types in Rust and how to perform operations on these. Section 2.3.1. Integers and decimal or floating point numbers. Rust uses a relatively conventional syntax for creating integers, 1, 2, etc., and floating point numbers, 1.0, 1.1, etc. Operations on numbers use infix notation, meaning that numeric expressions look like those that you're used to seeing in most programming languages. To operate on multiple types, Rust also allows the same token, plus, for addition. This is called operator overloading. Some notable differences from other languages follow. Rust includes a large number of numeric types. You will become used to declaring the size in bytes, which affects how many numbers the type can represent and whether your type is able to represent negative numbers. Conversions between types are always explicit. Rust does not automatically convert your 16-bit integer to a 32-bit integer. Rust numbers can have methods. For example, to round 24.5 to the nearest integer, Rust programmers use 24.5_f32.round rather than round 24.5_f32. Here, the type suffix is required because a concrete type is necessary. To start, Let's consider a small example. You'll find the code in ch2/ch2-intro-2-numbers.rs in the examples for this book. Listing 2.3 prints these few lines to the console. Section 2.3.2. Integers with base 2, base 8, and base 16 notation. Rust also has built-in support for numeric literals that allow you to define integers in base 2, or binary, base 8, octal, and base 16, or hexadecimal. This notation is always available within the formatting macros like println! Listing 2.4 demonstrates the three styles. You can find the source code for this listing in ch2/ch2-non-base2.rs. It produces the following output. In binary, or base 2 numerals, 0b11 equals 3, because 3 equals 2 times 1 plus 1 times 1. With octal, or base 8 numerals, 0036 equals 30, because 30 equals 8 times 3 plus 1 times 6. And with hexadecimal, or base 16 numerals, 0x12c equals 300, because 300 equals 256 times 1 plus 16 times 2 plus 1 times 12. Table 2.1 shows the types that represent scalar numbers. Rust contains a full complement of numeric types. The types are grouped into a few families. Signed integers, I, represent negative as well as positive integers. Unsigned integers, U, only represent positive integers, but can go twice as high as their signed counterparts. Floating point types, F, represent real numbers with special bit patterns to represent infinity, negative infinity, and not a number values. Integer width is the number of bits that the type uses in RAM and in the CPU. Types that take up more space, such as U32 versus I8, can represent a wider range of numbers. But this incurs the expense of needing to store extra zeros for smaller numbers, as Table 2.2 shows. Although we've only touched on numbers, we nearly have enough exposure to Rust to create a prototype of our pattern matching program. But let's look at comparing numbers before we create our program. Section 2.3.3. Comparing numbers. Rust's numeric types support a large suite of comparisons that you're probably familiar with. Enabling support for these comparisons is provided by a feature that you have not encountered yet. It is called traits. Table 2.3 summarizes the comparison operators available to you. Footnote 2. For the curious and eager, the traits involved here are std, cmp, partial ORed, and std, cmp, partial EQ. That support does include a few caveats. We'll look at these conditions in the rest of this section. Impossible to compare different types. Rust's type safety requirements prevent comparisons between types. For example, this code does not compile. To appease the compiler, we need to use an as operator to cast one of the operands to the other's type. The following code shows this typecast, B as I32. It's safest to cast the smaller type to a larger one, for example, a 16-bit type to a 32-bit type. This is sometimes referred to as promotion. In this case, we could have demoted down to a U16, but such a move is generally more risky. Warning. Using typecast carelessly will cause your program to behave unexpectedly. For example, the expression 300_I32 as I8 returns 44. In some cases, using the as keyword is too restrictive. It's possible to regain fuller control over the type conversion process at the cost of introducing some bureaucracy. The following listing shows a Rust method to use instead of the as keyword when the conversion might fail. Listing 2.5 introduces two new Rust concepts, traits and error handling. On line 1, the use keyword brings the std convert try into trait into local scope. This unlocks the try_into method of the b variable. We'll bypass a full explanation of why this occurs for now. In the meantime, consider a trait as a collection of methods. If you are from an object-oriented background, traits can be thought of as abstract classes or interfaces. If your programming experience is in functional languages, you can think of traits as type classes. Line 7 provides a glimpse of error handling in Rust. b.try_into returns an i32 value wrapped within a result. Result is introduced properly in Chapter 3. It can contain either a success value or an error value. The unwrap method can handle the success value and returns the value of b as an i32 here. If the conversion between U16 and I32 were to fail, then calling unsafe would crash the program. As the book progresses, you will learn safer ways of dealing with result rather than risking the program's stability. A distinguishing characteristic of Rust is that it only allows a type's methods to be called when the trait is within local scope. An implicit prelude enables common operations such as addition and assignment to be used without explicit imports. Tip: to understand what is included in local scope by default, you should investigate the std prelude module. Its documentation is available online at this link. Floating point hazards. Floating point types, F32 and F64 for example, can cause serious errors for the unwary. There are at least two reasons for this. These often approximate the numbers that they're representing. Floating point types are implemented in base 2, but we often want to calculate numbers in base 10. This mismatch creates ambiguity. Moreover, although often described as representing the real numbers, floating point values have a limited precision. Representing all of the reals would require infinite precision. These can represent values that have unintuitive semantics. Unlike integers, floating point types have some values that do not play well together, by design. Formally, these only have a partial equivalence relation. This is encoded in Rust's type system. F32 and F64 types only implement the std_cmp partial EQ trait, whereas other numeric types also implement std_cmp EQ. To prevent these hazards, here are two guidelines to follow. Avoid testing floating point numbers for equality. Be wary when results may be mathematically undefined. Using equality to compare floating point numbers can be highly problematic. Floating point numbers are implemented by computing systems that use binary or base 2 mathematics, but are often asked to perform operations on decimal or base 10 numbers. This poses a problem because many values we care about, such as 0.1, have no exact representation in binary. Footnote A. If this is confusing to think about, consider that many values, such as 1/3, have no exact representation within the decimal number system. To illustrate the problem, consider the following snippet. Should it run successfully or should it crash? Although the expression that is being evaluated, 0.1 plus 0.2 equals 0.3, it is a mathematical tautology. It crashes on most systems that run it. But not all. It turns out that the data type can affect whether the program succeeds or fails. The following code, available at this link, interrogates the internal bit patterns of each value to find where the differences lie. It then performs the test in the previous example against both F32 and F64 types. only one test passes. When executed, the program successfully generates the short report that follows, which reveals the error. After that, it crashes. Significantly, it crashes on line 14 when it compares the result of the F64 values. Generally speaking, it is safer to test whether mathematical operations fail within an acceptable margin of their true mathematical result. This margin is often referred to as the epsilon. Rust includes some tolerances to allow comparisons between floating point values. These tolerances are defined as F32 epsilon and F64 epsilon. To be more precise, it is possible to get closer to how Rust is behaving under the hood, as the following small example shows. In the example, what actually happens is interesting, but mostly irrelevant. The Rust compiler actually delegates the comparison to the CPU. Floating point operations are implemented using bespoke hardware within the chip. Footnote B. Illegal or undefined operations trigger a CPU exception. You will read about those in Chapter 12. Operations that produce mathematically undefined results, such as taking the square root of a negative number, negative 42.0.sqrt, present particular problems. Floating point types include not a number values, represented in Rust syntax as nan values, to handle these cases. Nan values poison other numbers. Almost all operations interacting with nan return nan. Another thing to be mindful of is that, by definition, nan values are never equal. This small program will always crash. To program defensively, make use of the is_nan and is_finite methods. Inducing a crash, rather than silently proceeding with a mathematical error, allows you to debug close to what has caused the problem. The following illustrates using the is_finite method to bring about this condition. Section 2.3.4. Rational, complex numbers, and other numeric types. Rust's standard library is comparatively slim. It excludes numeric types that are often available within other languages. These include many mathematical objects for working with rational numbers and complex numbers, arbitrary size integers and arbitrary precision floating point numbers for working with very large or very small numbers, fixed point decimal numbers for working with currencies. To access these specialized numeric types, you can use the num crate. Crates are Rust's name for packages. Open source crates are shared at the crates.io repository, which is where Cargo downloads num from. Listing 2.6 demonstrates adding two complex numbers together. If you're unfamiliar with the term complex numbers, these are two-dimensional, whereas numbers that you deal with in day-to-day are one-dimensional. Complex numbers have a real and imaginary parts and are denoted as real plus imaginary I. For example, 2.1 plus minus 1.2i is a single complex number. That's enough mathematics. Let's look at the code. Footnote 3. Mechanical engineers use J rather than I. Here is the recommended workflow to compile and run listing 2.6. 1. Execute the following commands in a terminal. 2. For those readers who prefer to learn by doing everything by hand, the following instructions will achieve the same end result. A. Execute the following commands in a terminal. B. Add version 0.4 of the num crate to the dependencies section of cargo.toml. That section will look like this. C. Replace src/main.rs with the source code from listing 2.6, available at ch2/ch2-complex/src main.rs. D. Execute cargo run. After several lines of intermediate output, cargo run should produce the following output. Some points from the listing are worth pausing to consider. The use keyword pulls crates into local scope, and the namespace operator, : restricts what's imported. In our case, only a single type is required, complex. Rust does not have constructors. Instead, every type has a literal form. You can initialize types by using the type name, complex, and assigning their fields, RE and IM, values, such as 2.1 or -1.2, within curly braces. Many types implement a new method for simplicity. This convention, however, is not part of the Rust language. To access fields, Rust programmers use the dot operator. For example, the num : complex : complex type has two fields. RE represents the real part and IM represents the imaginary part. Both are accessible with the dot operator. Listing 2.6 also introduces some new commands. It demonstrates two forms of initializing non-primitive data types. One is a literal syntax available as part of the Rust language, line 4. The other is the new static method, which is implemented by convention only and isn't defined as part of the language, line 5. A static method is a function that's available for a type, but it's not an instance of that type. Footnote 4. Although Rust is not object-oriented, it's impossible to create a subclass, for example. Rust makes use of some terminology from that domain. It's common to hear of Rust programmers discussing instances, methods, and objects. The second form is often preferred in real-world code because library authors use a type's new method to set defaults. It also involves less clutter. Shortcut for adding a third-party dependency to a project. I recommend that you install the cargo edit crate to enable the cargo add subcommand. You can do this with the following code. Up to this point, we have manually added dependencies to cargo.toml. The cargo add command simplifies this process by editing the file correctly on your behalf. We've now addressed how to access built-in numeric types and types available from third-party libraries. We'll move on to discussing some more of Rust's features. Section 2.4, Flow Control. Programs execute from top to bottom, except when you don't want that. Rust has a useful set of flow control mechanisms to facilitate this. This section provides a brief tour of the fundamentals. Section 2.4.1, 4. The central pillar of iteration. The for loop is the workhorse of iteration in Rust. Iterating through collections of things, including iterating over collections that may have infinitely many values, is easy. The basic form is. This basic form makes each successive element in container available as item. In this way, Rust emulates many dynamic languages with an easy-to-use, high-level syntax. However, it does have some pitfalls. Counterintuitively, once the block ends, accessing the container another time becomes invalid. Even though the container variable remains within local scope, its lifetime has ended. For reasons that are explained in Chapter 4, Rust assumes that container is no longer needed once the block finishes. When you want to reuse container later in your program, use a reference. Again, for reasons that are explained in Chapter 4, when a reference is omitted, Rust assumes that container is no longer needed. To add a reference to the container, prefix it with an ampersand, as this example shows. If you need to modify each item during the loop, you can use a mutable reference by including the MUT keyword. As an implementation detail, Rust's for loop construct is expanded to method calls by the compiler. As the following table shows, these three forms of for each map to a different method. Anonymous loops. When a local variable is not used within a block, by convention, you'll use an underscore. Using this pattern in conjunction with the underscore exclusive range syntax underscore n.m and the inclusive range syntax n.m makes it clear that the intent is to perform a loop for a fixed number of times. Here is an example. Avoiding managing an index variable. In many programming languages, it's common to loop through things by using a temporary variable that's incremented at the end of each iteration. Conventionally, this variable is named I for index. A Rust version of that pattern is this is legal Rust. It's also essential in cases when iterating directly over collection via for item in collection is impossible. However, it is generally discouraged. The manual approach introduces two problems with this. Performance. Indexing values with the collection index syntax incurs runtime cost for bounds checking. That is, Rust checks that index currently exists within collection as valid data. Those checks are not necessary when iterating directly over collection. The compiler can use compile time analysis to prove that illegal access is impossible. Safety. Periodically accessing collection over time introduces the possibility that it has changed. Using a for loop over collection directly allows Rust to guarantee that collection remains untouched by other parts of the program. Section 2.4.2. Continue, skipping the rest of the current iteration. The continue keyword operates as you would expect. Here is an example. Section 2.4.3. While, looping until a condition changes its state. The while loop proceeds as long as a condition holds. The condition, formerly known as a predicate, can be any expression that evaluates to true or false. This non-functioning snippet takes air quality samples, checking to avoid anomalies. Using while to stop iterating once a duration is reached. Listing 2.7, source code available at this location, provides a working example of while. It isn't an ideal method for implementing benchmarks, but can be a useful tool to have in your toolbox. In the listing, while continues to execute a block when a time limit is not reached. Avoid while when endlessly looping. Most Rust programmers avoid the following idiom to express looping forever. The preferred alternative is to use the loop keyword, explained in the next section. Section 2.4.4. Loop, the basis for Rust's looping constructs. Rust contains a loop keyword for providing more control than for and while. Loop executes a code block again and again, never stopping for a tea or coffee break. Loop continues to execute until a break keyword is encountered or the program is terminated from the outside. Here is an example showing the loop syntax. Loop is often seen when implementing long-running servers, as the following example shows. Section 2.4.5. Break, aborting a loop. The break keyword breaks out of a loop. In this regard, Rust generally operates as you are used to. Break from nested loops. You can break out of a nested loop with loop labels. A loop label is an identifier prefixed with an apostrophe, like this example shows. Footnote 5. This functionality is also available with continue, but it's less common. Rust does not include the goto keyword, which provides the ability to jump to other parts of the program. The goto keyword can make control flow confusing, and its use is generally discouraged. One place where it is still commonly used, though, is to jump to and clean up a section of a function when an error condition is detected. Use loop labels to enable that pattern. Section 2.4.6. If else, and else. Conditional branching. So far, we've indulged in the exciting pursuit of looking for numbers within lists of numbers. Our tests have involved utilizing the if keyword. Here's an example. If accepts any expression that evaluates to a Boolean value, e.g., true or false. When you want to test multiple expressions, it's possible to add a chain of if-else blocks. The else block matches anything that has not already been matched. For example, Rust has no concept of truthy or falsy types. Other languages allow special values such as 0 or an empty string to stand in for false, and for other values to represent true, but Rust does not allow this. The only value that can be used for true is true, and for false, use false. Rust is an expression-based language. In programming languages from this heritage, all expressions return values and almost everything is an expression. This heritage reveals itself through some constructs that are not legal in other languages. In idiomatic Rust, the return keyword is omitted from functions as shown in the following snippet. For example, Rust programmers assign variables from conditional expressions. This can be extended to other blocks including match, like this. Perhaps most surprisingly, the break keyword also returns a value. This can be used to allow infinite loops to return values. You may wonder what parts of Rust are not expressions and thus do not return values. Statements are not expressions. These appear in Rust in three places. Expressions delimited by the semicolon, binding a name to a value with the assignment operator, type declarations, which include functions, fn, and data types created with the struct and enum keywords. Formally, the first form is referred to as an expression statement. The last two are both called declaration statements. In Rust, no value is represented as open-close parentheses, the unit type. Section 2.4.7. Match. Type-aware pattern matching. While it's possible to use if-else blocks in Rust, match provides a safer alternative. Match warns you if you haven't considered a relevant alternative. It's also elegant and concise. Match offers a sophisticated and concise syntax for testing multiple possible values. Some examples are inclusive ranges, 10 ... equals 20, to match any value within the range. A Boolean or, pipe symbol, will match when either side matches. The underscore to match everything. Match is analogous to the switch keyword in other languages. Unlike C's switch, however, match guarantees that all possible options for a type are explicitly handled. Failing to provide a branch for every possible value triggers a compiler error. Additionally, a match does not fall through to the next option by default. Instead, match returns immediately when a match is found. Listing 2.8 demonstrates a larger example of match. The source code for this listing is at this location. The code prints these two lines to the screen. The match keyword plays an important role within the Rust language. Many control structures, like looping, are defined in terms of match under the hood. These really shine when combined with the option type that is discussed in depth in the next chapter. Now that we have taken a good look at defining numbers and working with some of Rust's flow control mechanisms, let's move on to adding structure to programs with functions. Section 2.5. Defining functions. Looking back to where the chapter begins, The snippet in listing 2.2 contained a small function, add. Add takes two I32 values and returns their sum. The following listing repeats the function. For the moment, let's concentrate on the syntax of each of the elements in listing 2.9. Figure 2.2 provides a visual picture of each of the pieces. Anyone who is programmed in a strongly typed programming language should be able to squint their way through the diagram. Rust's functions require that you specify your parameters types and the function's return type. This is the foundational knowledge that we'll need for the majority of our work with Rust. Let's put it to use with our first non-trivial program. Section 2.6, Using References. If you have only used a dynamic programming language